As our second case, we're going to consider the case when the ideal A is not contained in this list of algebra H consisting of all diagonal matrices in SL and C. And our goal here is to show that the ideal A can only be the whole space G. Since this ideal A is contained in G, and G, by our root space decomposition theorem, we will abbreviate as RSDT. This decomposition, remember, is the direct sum of H with the direct sums of the one-dimensional list of algebras C times E sub ij's for all pairs I not equal to J. To show that A is equal to the whole space G, it suffices to show that E sub ii minus E sub jj and E sub ij all contained in the ideal A for any ij. Because remember, those elements for I not equal to j will span H, and those elements will span the rest of the direct sum components. If you can prove this for all I not equal to j, then you proved that A must consist of all vectors in G by this root space decomposition. Actually, we are just using this in a very trivial way. We are just considering this as a decomposition of a complex finite dimensional linear space. Now, let capital X be H plus the linear combination of E sub ij's with this part not equal to 0 be an element in A. We are able to make this part not equal to 0 simply because of our assumption that A is not contained in H. Now we are going to make the following claim. Claim E sub in is in the ideal A, or E sub n1 is in A. Of course, those two things could happen simultaneously. We're just claiming that at least one of those two things will happen. As a matter of fact, once this claim is proved, we'll be able to finish the proof of the whole theorem on the simplicity of SL and C. Namely, this claim will imply that A is equal to G in this situation. So, let us first show how this claim implies that A is equal to G. Once this claim is true, say one of those two things happens. Say E sub in is in A, The idea for the rest of the proof is the following. We're going to use some dominoes effect in math. Namely, in order to prove that a group of elements satisfies some property, it suffices to check that property just for one or two elements in that group. And establish the relations between these one or two elements and the rest of the elements. And in this proof, we're going to just start with E sub in in A, and we'll use the Lie bracket relations of those E sub ij's to show that all the other E sub ij's are also in A. And we are also going to prove that all the E sub ii minus E sub ij's are in A, from which we'll be able to conclude that A is equal to G.